Welcome back. This is Mr. Hassan's Maths channel. I'm now answering a question from one of the legacy papers from the old syllabus before the P2 paper. This is from October 2017. It's a C12 paper, Core Mathematics, which is now known as Pure Mathematics. And this relates to P2 material. The C12 used to be P1 and P2 kind of like mixed up together. This particular question, number 9 from this year, is about P2, and I'm answering this particular question especially for part C, which relates to a question which a lot of students are asking about, which I can't upload at the moment at the time of doing this because it's one of the locked papers, but it relates to that paper in terms of what I'm going to explain will help you to understand hopefully how to tackle one of the questions on that paper. Now, it says here, so that's going to be in part C, and I'll put a timestamp for that for those of you who are in a hurry to watch that before your exam tomorrow, for those who are watching in 2023. Now, given that a is a constant, a is greater than 1, sketch the graph of y equals a to the power of x. So a is a number. So this is like an exponential curve, and exponential curves look like this if a is greater than 1, and they look like this if a is less than 1. Okay, if a is less than, you could not less than 1, sorry. If a is between 0 and 1. If it's greater than 0 and less than 1, it looks like this. It's like if it's a fraction, like a half or something like that. Okay, so that's how when a is greater than 1, it looks like this. So for example, 2 to the power of x would look like this. Y equals 2 to the power of x would look like this. But y equals a half to the power of x would look something like this. Okay, because this a half is the same as 2 to the power of minus 1. So a half x is the same as 2 to the power of minus x. So if you compare that to y equals 2 to the power of x, which looks like this, this is where the x coordinates have changed their sign. So it's like a reflection in the y-axis. The x coordinates become, the y coordinates stay the same. So this point will have the same y coordinate, but the x coordinate will switch. So we end up over here. So this is like a reflection in the y-axis, but this is no problem. This is the normal type of curve. Y equals something to the power of x, where this number is greater than 1. It's going to have this kind of exponential increasing curve. Okay, so we don't really have to worry about that other stuff in case it comes up. That's just a little explanation. So y equals to the power of x. We're going to draw the sketch and show the coordinates of the point where the graph crosses the y-axis. Well, that's pretty simple. You can draw our axes. We know that this graph will never go below the x-axis. It can never be even touch the x-axis. It's going to be like that. This is the x-axis, which is y equals 0. This is y-axis, which is x equals 0. It's going to have this type of shape. Okay, it's going to look like this. Exponential increase. And the point where it crosses the y-axis, of course, is when x equals 0. When x equals 0, if you put x equals 0 in here, you have a to the power of 0, which is 1. So they all pass through 1 in this form. So 2 to the power of x, 3 to the power of x, 10 to the power of x, even a half to the power of x, which goes like this, they'll always pass through 0, 1 on the y-axis. So show the coordinates. I'll write it in coordinate form. The y-axis, if they said drawing asymptotes, then y equals 0, which is x-axis, would be an asymptote, which you might have to mark. But they didn't ask you to do that. So that's fine for part A. That's the answer to part A. 2 marks, and that's done. Now for part B, here we have a table which shows the corresponding values of x and y for 2 to the power of x. So they've given us the values already. The table's done for us already. We don't have to put any values in. Okay, we want to use the trapezium rule with all the values of y from the table to find an approximate value to 2 decimal places for this. So what I'll do is I'll take a little sketch of this curve. I'll take a little screenshot of this curve, and I will use it to just illustrate how the trapezium rule works. Okay, so I'll just plonk this down here, make it smaller, and I'll show you how the trapezium rule can be applied, what the trapezium rule actually is. So basically, between -4 and 4, we want to find the integral of 2 to the power of x with respect to x, which is like finding the area under this curve between -4 and 4. Okay, so we don't want to use integration because, in fact, we can't use integration at this stage in our understanding of integration. We don't know how to integrate something of this form, so we have no choice but to use the trapezium rule as one way of estimating. So between -4 and 4, we want to find this area. That's what we want to do. That's our objective. So what they've done is they've given us a table of values going up in steps of 2s. So you have -4, -2, 0, 2, and 4. These are the steps they've given us. So it's like what they're doing is they're forming these trapeziums. One here, one there, and the last one there. Equally spaced trapeziums. Each of those trapeziums are 2 units wide. So the difference between the distance between the parallel sides of these trapeziums is 2. You notice the trapeziums are kind of like this. So actually the top of the trapezium will kind of pass over the curve slightly. So what we'll get is a slight overestimate when we use the trapezium rule, because we're finding an area which is slightly above the curve. All right, so you can see that drawing these trapeziums gives you a kind of a rough approximation of these sections. So when you put these trapeziums in here, we'll end up finding the area of each of these trapeziums, adding them together, and that will give us an approximate area of the curve between -4 and 4. Okay, we know that the trapezium is given, the area of a trapezium is given by the distance between the parallel sides, which is h, divided by 2 times the sum of the parallel sides. So this is like your h, the distance between the parallel sides is your h. So that's over here. These are our h's, right? Which are all 2. So there's no need for us to go and fluff around and say, okay, we got, all right, 4 minus 4 divided by, and then people get messed up. They say, oh, divided by 5, because they see 5 numbers here. No, there are 4 trapeziums. There are 5 ordinates, 5 lines, but 4 trapeziums. 1, 2, 3, 4. The trapeziums are what comes between these values. So you don't need to, there's no need for us to even work that out, because we can see the distance between the parallel sides from these numbers. The difference between the x values is the distance between the parallel sides. They're all 2. So the h is equal to 2 here, right? We don't have to work it out. It's given to us, right? If they told us, you know, divide this between -4 and 4 into 5 strips or 4 strips of equal length, then we'd have to work out what it is. We'd have to say, okay, 4 minus -4 divided by 4, and you'd work out exactly, you know, what the width of each strip is, and then you would put the table of values in. Here, they've given everything to us. There's no need for us to work out what h is. H is this. This is h. It's given to us. So there's no need to, you know, make that mistake like some students do. So now, when we use the trapezium rule, I'm just going to show you how it works. What we're doing here is we're adding all these trapeziums together. So for the first trapezium, it's going to be h over 2. H over 2 times, you're going to have this ordinate plus that ordinate. So this ordinate is basically the y value for this x value on this curve. So it's basically that value there. So let's call this y1, let's call this y2, let's call this y3, y4, and y5. There's 5 ordinates for trapeziums. So for the first trapezium, it will be h over 2 times y1 plus y2. I'm just going through the process so everyone understands what the trapezium rule actually is. Okay, if you understand this, you can skip this for, you know, to the next part if you have no problem with this. For the second trapezium is h over 2 times, so this one will be the distance between the parallel sides, which is h divided by 2 times y2 plus y3. Plus, and the same thing for the third trapezium here, you'll have h over 2 times y3 plus y4. And for the last trapezium, you'll have h over 2 times y4 plus y5. And so basically what we got here, we have a common factor of h over 2 in all of them. So that's common. And then if we take that out, we're left with y1 plus y2 plus y2 plus y3 plus y3 plus y4 plus y4 plus y5. Notice that y2 is appearing twice, y3 is appearing twice, y4 is appearing twice, but y1, this line and this line only appear once because they're only in the first and the last trapeziums. Y2 is in both these trapeziums, y3 is in these 2 trapeziums, and y4 is in those 2 trapeziums. So basically our formula becomes h over 2, and you have y1 and y5 appearing just once, and then everything else appears twice, so it's 2 times y2 plus y3 plus y4. That's where the trapezium rule comes from. Just finding the area of each of these trapeziums and simplifying it. You don't have to do this. This is given to us in the formula book. I just want you to understand where it comes from. So the area of the trapezium is going to be given by the distance between the parallel sides, which is 2. Okay. Divided by 2. Let me just write this a bit neatly. Divided by 2 times the sum of the parallel sides. So I'm going to take the first and the last one, which is this and this, and add them together without multiplying by 2. So I'll put 0.0625 plus 16 plus 2 times everything else in the middle, which is 0.25 plus 1 plus 4. That will give us an estimate of this area. Okay, so this area, the estimate's going to be, this will be 1 times all of that. So I can just stick all of that in my calculator. So where's my calculator gone? Come on. There we are. So we have 0.0625. Is it 0.0? Just to make sure. Yep, plus 0.2, plus 16. That was the other one that occurred once. Plus 16. Plus 2 times the ones in between, which is 0.25. Plus 1 plus 4, which is 5. Close that bracket. And that's multiplied by 1, so there's no problem. So it's 425 over 16. I'll write it like this, and then I'll round it 2 decimal places. Okay, so that's equal to SD 26.5625, 26.5625. Yeah, which gives us 26.56. Why? Because they ask us to give it to 2 decimal places. So be very careful not to mess that up. So 26.56 square unit. Well, they just said find the value of the integral. They didn't say the area. So we could leave it as a value to 2 decimal places. And there's the answer to part B of this question. Okay, now for part C. Now in this part of the question, we have to be very careful. It says use the answer to part B. Use the answer to part B to find an approximate value for this expression. Okay, so I'm going to go through this in this way, and I'm going to also go through this in a way that's going to help those students to understand something from one of the other papers after at the end. So in this particular thing, what we have so far, we have between -4 and 4 of 2 to the power of x is equal to, and its exact value was 425 over 16. So I'll use that for now, and you can use that or the rounded value, but it's better to, I think, use the kind of more exact value. So that's the integral of, that's an approximate value for the integral of 2 to the power of x between -4 and 4 using the trapezium rule. All right. So this is the answer to part B. Okay. So we want to use this answer to find the value of this. Now, what they don't intend for you to do is to use the trapezium rule all over again. That's not what they want you to do. They want you to express 2 to the power of x plus 2 in terms of 2 to the power of x. Now, that's quite easily done if we know the rule of indices. If we think backwards, we know that when we multiply 2 numbers in index form, we end up with the same base, but the powers added. So here, this could have started off as 2 to the power of x multiplied by 2 to the power of 2, which is like 4 times 2 to the power of x, because 2 to the power of 2 is 4. So this can be rewritten between -4 and 4 of 2 to the power of x plus 2 with respect to x can be rewritten as the integral between -4 and 4 of 2 to the power of x times 4. Okay, you can rewrite it like this. And one of the things about integrals, as I mentioned a few times already, is that when you have something times your variable, you can write that constant outside the integral sign. So this is 2 to the power of x, which is our variable. The constant is 4, which is multiplying it. That will give me the same answer whether I wrote this outside or wrote this inside. So now this is exactly what we have there. This is now the same as that. So I can simply replace this with 425 over 16. So this is 4 times 425 over 16. And that will give us our answer. So it's 425 over 4, which we can round if we want to. 425 divided by 4 gives us 106.25. So we can write it like that, 106.25. We can leave it in the exact form, no problem. It doesn't tell us what to do. We could write it as 106.3. That's fine. Okay, it didn't tell us to give us to round it to any particular value, so that's fine. So that's part C. Now I'm going to come back to part C and show you something different in part C at the end of this little section, but we're going to do part C part 1. C part 2 is something also which we can understand from integration, that when I integrate 2 separate functions together, if they're 2 separate functions and I integrate them, I can split them up into separate integrals. So I can have the integral of f of x with respect to x plus the integral of g of x with respect to x. Same with differentiation. I can integrate them and differentiate them separately. So 3 is something I'm going to integrate. It's a term. It's not like a constant which is multiplying. It's a constant which is added to the whole expression here. So I have to integrate this separately from this. It's not like 4 times 2 to the power of x. Like if I integrate 2x squared, yeah, that gives me 2x cubed over 3. If I integrate 2 times the integral of x squared, that also gives me 2x cubed over 3. Same thing, right? Because it's multiplying. But if it's 2 plus x squared, if I integrate it, that integrates separately from that. So what I'm trying to say here is that when you have something added or subtracted, you have to integrate them, and you integrate them separately. That's actually what we do. We don't write it out like that, but that's what we do. We integrate this, then we integrate that. So that understanding will help us if we're trying to split this up into a form where we need this on its own. So what I can do is I can say this is the same as saying the integral between minus 4 and 4 of 3 with respect to x plus the integral between minus 4 and 4 of 2 to the power of x with respect to x. Now this is again exactly the same as what we have, okay, which is equal to 425 over 16. So I know that this is the same now, or approximately equal to 425 over 16, which we worked out in part A, the estimate of that using the trapezium rule. And something like 3 dx, we can integrate that easily. The integral of 3 with respect to x is 3x. So this becomes 3x. You have the limits between 4 and minus 4 plus, and this is replaced by 425 over 16. So we have 3 times 4, which is 12. So you have 3 times 4 minus 3 times minus 4 plus 425 over 16. That gives you 12 minus 12, which is plus 12, plus 425 over 16, which is 24 plus 425 over 16. So we worked that out. It's just 24 plus that last answer that we got, which is this. Okay, so it's 24 plus that last answer, which is 809 over 16. So that's 809 over 16, which we'll round it to 2SF like the last one, 50.56. So that's 50.56. And that's the answer for part 2. And that concludes this question. Now, what I've just done here, okay, what I've just done here for part 2, this could have been the integral between minus 4 and 4 of f of x plus 3 with respect to x. Now, hopefully that will make you understand. Okay, if we had, the original thing, which is 2 of x, 2 to the power of x between minus 4 and 4 with respect to x, if we call that f of x between minus 4 and 4, then that will help you understand what to do in the particular question that I'm referring to. You can take this and split it up into 2 parts. You have the integral of f of x plus the integral of 3 with respect to x between minus 4 and 4, and you split it up like that. So whatever you got for that in the first part, you add it to the integral of whatever's added to it when it's outside the function. This is f of x plus something. But what do you do when it's, and in the question that you'll see like this, this is like fx plus 2. If you compare, if f of x is equal to 2 to the power of x, then this 2 to the power of x plus 2 is like fx plus 2, where it's inside the function. Now you'll notice that this from P1 is a transformation of minus 2, 0. Everything goes back 2 spaces. So in a question like this, when they're wanting you to understand about transformations, what they're going to do is they won't have minus 4 and 4, but they'll have this as minus 6 and 2. And you'll notice that in the question that I'm trying to refer you to, the difference, that number that's added or subtracted here, the opposite will happen to these limits. Why? Because basically what's happening is this. Okay, the whole thing is shifting 2 spaces to the left here. So if I draw this crudely, this line, okay, so what you'll notice is they will have the limits between minus 6 and 2 instead of minus 4 and 4, because when you move that graph 2 units to the left, that area will remain the same. Okay, so let me just try and illustrate that here. It's like the whole thing is shifting. So if I make that line here and here, and I connect those lines to this graph. Let me just group them together. Okay, so this thing that I've just grouped together, you see this whole area, if I move this thing, okay, and it goes back to -6 and 2, that area is the same. Okay, let me put the -6 over here. That area is the same. See, the area under here and the area between -6 and 2 is exactly the same area. The whole thing has shifted 2 spaces to the left. So that's what, when you have fx plus 2, so the integral of fx plus 2 between -6 and 2 will be the same as the integral of fx between -4 and 4. They have the same area. Okay, so when you get a question like this where there's a transformation inside the function, it's not added to the whole thing, it's inside the function, that causes a horizontal shift of 2 units to the left. And you'll notice that each of the limits will have changed to be 2 units less because it's going to the left by 2 units. So the area there and the area under between -6 and 2 and the area between -4 and 4 will be the same. And that's the understanding you need for the question that all of you are asking about, which I can't put up at the moment. So I hope that is the best, the best way for me to help you. For those, some of you are coming afterwards, who will have the privilege of seeing the question from January 2023. You won't understand why I'm going through this, but you'll see it in January 2023 why, when that comes up, why I'm going through this, because that's like a question that a lot of students are asking about. So hopefully that will give you an understanding of how to deal with that question. And yeah, that's the end of this video. Thank you very much for watching. Other questions from this particular paper, October 2017 of C12, if I answer them, if anyone asks me questions from it, I'll put in the playlist that will appear over here. Other questions from the trapezium rule of P2, I'll put in the playlist over here. You can subscribe to my channel by clicking on this link, and you can watch videos or a video which explains to you how to use my channel to find things more efficiently. That link will appear over here. Thank you for watching and see you soon.